Hi everyone, my name is Eldy Lazaro, master's student in design at UC Davis, graduating this year, and together with professors Hao-Chuan, Wang, and Katia Vega, contributed to the paper I'm presenting today, introducing the sustainable prototyping lifecycle for digital fabrication to designers. Prototyping with digital fabrication not only creates material waste, but also requires energy consumption to run the machines, which at the same time generates CO2 emissions. It's our concern of how sustainable and environmentally friendly the practice of digital fabrication is, as well as the materials used for prototyping. We asked in this paper how to introduce sustainable prototyping with digital fabrication to designers, makers, and researchers. Previous research in the HCI community aimed to define the scope and role of HCI researchers regarding sustainability. In addition, environmental impact of digital fabrication research included how to optimize energy use of machines, methods, and alternative materials to address this issue. Similarly, biodesign incorporates the use of living materials such as fungi, algae, or bacteria to enhance sustainable design. This paper introduces the sustainable prototyping life cycle for digital fabrication, an adaptation from the life cycle assessment method to support designers' decision-making for sustainable prototyping. This cycle reveals the environmental impact of digital fabrication in every phase of prototyping. It has 4 phases: raw materials acquisition, manufacture and distribution, use, and end of life. Our aim is to increase environmental awareness in prototyping and highlight the importance of designers' decision-making within each phase of the prototyping cycle. The first phase includes raw materials needed to make a prototyping material, the transportation of materials to manufacturing sites, and the energy usage and CO2 emissions generated in this phase. In our study, Mycelium-composite material, roots of fungi, is used as a sustainable prototyping material. It's heat-resistant, lightweight, shapeable, and naturally hydrophobic. These properties enable the material to embed electronics or prototype with digital fabrication. Mycelium can grow in agricultural waste, such as hemp, flax, or coffee grounds. However, energy consumption is required to sterilize the substrate to avoid molding. The second phase includes product manufacturing and assembly, packaging and transportation to final distribution. Energy, fuel consumption, and CO2 emissions are considered part of the environmental impact of our prototype, even if we don't have an active participation in the manufacturing process. In our study, the biofabrication process to make mycelium-composite material requires the use of cooking sheets as molds, an oven to dry the mycelium-composite sheets, and a hydraulic compressor to flatten the material in a desired thickness. The third phase includes energy consumption and CO2 emissions generated during a normal product life, required energy for maintenance, and product reuse. We made some laser cutting test cards to show the performance of the microsheets for digital fabrication. Here are some examples of prototyping product designs and interactive objects using mycelium sheets as material and laser cutting as digital fabrication technique. In our study, this phase includes the decision-making of materials and digital fabrication techniques. These decisions vary from low to high fidelity prototyping, and the number of iterations also add environmental impacts to the final prototype. The fourth phase includes waste management and end of life of products when they are recycled, landfill, or composted. Liquid waste, gas emissions, soil erosion, and degradation are some of the problems related to this phase. In our study, this phase includes the reuse and disposal of prototyping materials properly. For instance, making sure that PLA is disposed in a recycling bin or bio-based materials in a compost bin. Here you can see the degradation time of common prototyping materials when they end up in the landfill. Bio-based materials are compostable and they degrade in up to 90 days as any other organic waste. Great. The following section of the paper put the sustainable prototyping life cycle in action, with focus on the last 2 phases, use and end of life. 3 qualitative studies were conducted to see the potential of our proposal. We made an online survey to 60 advanced users of digital fabrication to understand the materials and techniques used. We conducted an interview to 10 design experts to envision the use and possibilities of bio-based materials for prototyping. And we conducted a sustainable focus workshop with 22 novice designers to understand their reasoning and decision-making in the prototyping process. In the online survey, we found that MDF is the most common material for digital fabrication, and laser cutting the most common technique used. We used the survey results to design the prototypes we were going to showcase in the interview to experts. We collected experts' reflection about mycelium composite materials for prototyping and best ways in which bio-based materials can be introduced to novice design students in a classroom setup. Experts agreed on prototyping is a wasteful process, and one of them suggested to use test cards to display the life cycle analysis of the material. We used experts' reflection to design a sustainable focused workshop with novice designers and to introduce bio-based materials as prototyping material for digital fabrication. Students were allowed to iterate up to 3 times and pick their preferred materials to laser cut in between mat board, acrylic sheets, plywood, and Mycelium-composite. Almost 90% of students chose Mycelium-composite for the first iteration, and only 30% of them for the final iteration. We discussed 4 main findings that emerged from our study. 1. Bio-based materials can be an enabler of sustainable prototyping because of its low impact in each phase of the cycle. Novice designers showed their understanding of low-impact materials during the workshop by using different materials in different stages of the prototyping process. Design experts rely on physical properties such as strength when choosing a material to prototype with. On the other hand, novices have shown to be more open to incorporate bio-based materials within their prototyping process anytime. Experts find the growing time of the material and not to have them available in the market as limitations of use. On the other hand, novice designers enjoy the experience of making their material for prototyping and looked at it as part of their learning process. 2. Experts, different than novices, showed a better understanding of the environmental impact of the use phase. They had a major concern about the amount of energy the machines consume in a single-use prototype. We discussed the fact that even though we came up with low-impact materials for prototyping in this study, we are still using the same machines for rapid prototyping regardless of the material. So we will be partially reducing our environmental impact. This becomes a limitation for designers who want to design sustainably within each phase of the cycle because the energy efficiency of the machines are not totally up to them. 3. Having zero waste should be the ultimate goal in sustainable prototyping because we are not always prototyping with bio-based materials. Optimizing the use of materials can be a start point. For example, making our design modular to have zero waste when laser cutting, reducing scraps of materials, or using softwares that optimize the laser cutting area. Novice designers found bio-based materials waste positive. However, that only happens when the waste is disposed in the right conditions. We have identified that waste management and recycling practices are issues that characterize the lack of sustainable practices in laboratories. That's why improving our disposal behavior becomes a first step to make the end-of-life phase optimal. 4. To have a more environmentally sustainable lab, we should be aware of the material's life cycle that we are using for prototyping. Acknowledge that all parts of the prototyping life cycle consume energy and generate CO2 emissions. There is a breakdown of energy associated with each life phase of the materials, and to optimize the environmental impact of prototyping, we should make the right decisions about materials and digital fabrication techniques. Introducing the cycle can prompt designers' decision-making of materials in their prototyping process. Our paper contributes with an adaptation of the LCA for digital fabrication with bio-based materials, which support designers' decision-making for sustainable prototyping. It reports the finding of qualitative studies that were used to gain understanding on the possibilities of intertwining bio-based materials with digital fabrication techniques, the current prototyping practices of different design groups, strengths and limitations on sustainable prototyping, and possibilities for introducing the cycle to digital fabrication practitioners. Finally, the implications for design practitioners, researchers, and educators to address environmental sustainability. This paper presents the manufacturing process of several digital fabrication prototypes with bio-based materials following the cycle. Bio-based materials for prototyping is a good start point, moving towards an environmentally sustainable making. However, other good practices must be involved in every phase of the cycle, such as reducing transportation distances, reducing the energy consumption in machines, or making sure we are using energy-efficient machines in our labs. Introducing topics such as sustainable prototyping could potentially influence novices' decision-making of materials in the long term, which goes beyond a classroom but future professional practice. Future works could implement the cycle using common materials or other bio-based materials that can be adapted and used for digital fabrication, provide a comparison of their environmental impacts, And finally, develop a tool that quantitatively calculates the environmental impact in each phase of the prototyping cycle. Thank you so much. Feel free to reach out if you have any questions. Bye.